you go to the Zoom meeting one at the bottom, Sarah.
Oh, now I thought all of this was set up. Oh, yeah, got it. Zoom
Yeah, go to
meeting.
that, then make sure at the bottom you'll be able to share. Go into that window there. Yeah, share screen.
Oh, yes, I
And
can
make
see
sure
it.
you select the window you want to share,
This one.
and then we're all good.
Right, we're sorted. I'll pop your slides on. There you go. It's all over to you, Amani. Go for it.
So hi everybody. My name is Amani Alanazen. I'm a PhD student at University of Leeds. I'm supervised by Dr. James Wilson and Dr. Serge Rule. I'm interested in corpus linguistics and utilizing its tools in studying academic writing and connectors. Yeah, and this is a piece or a part of my PhD thesis, which is only focusing on resultative connectors. So basically, first I'm going to introduce or give a brief introduction about what is sentence connectors. Then I'm going to discuss the methodology of that I've done to analyze resultative connectors. Then I'm going to show the results. Then I'm going to show the results, and after that, I'm going to tell you the conclusion that I reached.
It's that little window, and the middle one in that corner, the black one.
Yeah.
You click the exit, whatever, minimize things now. And then go back to
Share
your
the screen.
Make sure we're sharing the wrong one.
Try that one. Is that coming up?
Bit of a delay.
Yeah.
Close.
That was the same one as that one.
But it's not, because it's showing
Oh, I see.
got something wrong going.
Okay, I understand. Then it must be that we want to share screen. There we go. That might be tidier. Apologies.
Sorry. Okay. Now it's not moving.
You just click on that window with the mouse, and it'll sort itself out.
Thank you. So first, in academic writing, it is important to use to make sure that your text is coherent. And to do so, you should always use any method that makes the text coherent. And one of these methods is using sentence connectors, which I'm going to define. Sentence connectors are any word that's used to link other words, phrases, or paragraphs with semantic relations, so to make your text coherent. So what this is the definition of sentence connectors. So, and sentence connector has been introduced by Halliday and Cassens, and a lot of researchers use their method for way classification to do other classification of sentence connectors. The one I'm doing in my research is based on Craig et al. 1985, which classifies sentence connector in 7 major types, which are listing, resultative, influential, contrastive, transitional, summative, and appositive. And in this study, I'm going to analyze resultative only. So, what are resultative connectors? What are their definition? So resultative connectors, from the word result, gives the relation of cause and result. It's also sometimes some scholars call them causal connectors because it gives the cause and effect semantic relation. But I'm using resultative because I am using the framework of Craig et al. And why am I focusing on resultative connectors? I'm focusing on resultative connectors because it is believed that it is one of the most used logical connectors by students whether they are native or non-native speakers. The list I'm using here consists of 6 connectors, which are so, because, hence, accordingly, as a result, and therefore. Okay, so this is the methodology. In my study, I used 3 corpora. The first one is bulk, which consists of Arab students writing. It was compiled by the British University in Dubai, and most of the students there are either first year university students or the last secondary school. The corpora I'm comparing my corpus to, there are 2 subcorpora of the First International Corpus of Academic English. The first one is American, which here I describe as AM, and the second one is British, which I describe as BR. I filtered the corpora, all the 3 corpora, to make sure that they are similar. So here you can find a lot of journals, essays, reports, but I choose the best comparative essays to the students writing. And so at the end, this is the corpora I gained, the bulk, and how many words and types it consists, the AM, how many words and types it consists, and this is the American, this is the British. And to analyze these corpora, I use Sketch Engine, which is one of the corpus tools, and you can access it through this website. So in Sketch Engine, I use the concordance lines to make sure that every word or every connector is right and in its correct use. For example, we can say that many people use so, and this is the example I'm discussing, in different ways. And so that's why I manually printed all the lines and discarded all irrelevant occurrences. And for making sure that there is a significance of the frequency of words, I use the log likelihood statistical test to make sure if the significance is statistically important. So this is the results I gained. So these are the connectors I used, and this is the bulk and the AM, the log likelihood, and the bulk with the BR and the log likelihood. If you can see the plus sign, it means that there is an overuse of the connector, and here in the bulk. So if it's plus bulk, it means that Arab learners use this connector more than the native speakers. So generally, we can say that Arab learners prefer to use the because and so more than other resultative connectors. And this is for the British and the Americans. So they did not use, or did not prefer to use other types of connectors. They mainly focused on because. That's why we can say they overused it more than the native speakers. So now I'm going to discuss, we can see that it is one of the most used connectors by British students, not by the American students. And I will also discuss the position of the connector and Arab learners use. Mostly all learners, whether they are students, the native students or non-native, use use so in the middle and in the beginning of the sentence. We can say that no one of them use so at the end of the sentence, which means this is kind of correct use of so. Now, when we discuss the middle positioning by Arab learners, there was 409 occurrences of so in the corpus. 216 was used in the middle, preceded by a comma, 26 preceded by a full stop. If it's by a full stop, it means that they started the sentence with, so if it's by a comma, it means that it came in the middle. There were some other punctuation marks, which is a question mark, an exclamation mark, which we can say that it is a confusion for students. Like, why would they use such marks with so? And these are some examples of their use. We can say that their use with so were mainly correct. They use it at the middle of the sentence. Okay. So now I'm going to move to the conclusion. So I have arrived to the following conclusion. First, Arab students generally overuse resultative connectors compared to both native speakers, corpora. which we can say that both speakers or both native speakers do not rely on resultative connectors to convey the meaning of results. Sometimes they use, you can tell the meaning or they can convey the meaning without using any type of connectors. But for Arabs, they think that it is like a must to use a connector to link their sentences. And the second result is that most frequent connector is because, and students use it more frequently than native speakers. And that's because, why is that? Because students rely on easy connectors and they do not really try to alternate connectors, while we can say that native speakers use a different or alternative connectors, not only because. The third result is student preferred using the resultative connectors in the middle sentences, which we can say that because they do not feel that or they do not want to make mistakes, so they avoid making mistakes. That's why they try to use it in the middle, because they're not sure if they use it at the beginning what to do or what punctuations to use. So they prefer using it in the middle position since they feel more safe and accurate. The last one is students' attitude toward positioning, capitalization, and punctuation was confusing because this is because of the way of teaching, this is not the teacher's fault. We can say that the books and materials give the students a list of connectors, and students do actually, they think that the connectors are synonyms, so they use so, and sometimes they alternate it with as a result while they give two different meanings. And that's why they do not know what punctuation to use and when to use the punctuation. Okay, so this is the reference list, and thank you.
We're going to do some questions at the end, if that's all right. Thank you so much. It was really interesting. Thank you. Okay, so our next speaker is Christina.
Stop share.
Will be at the end. I'll just do the whole presentation link at the end.
Okay, so you're going to do, what do we need to what do I need?
The slides.
Yeah, so
Just
this
to share
one,
the slide.
so which one's yours? Do we know? Not that one. Ah, this one.
Yeah. Yeah.
Okay. Now, screen, but make sure that I share the, now is that the PowerPoint? Yeah. Jonathan. Go, Christina, go for it. Thank you.
Hello everyone. So today I'll be talking about our package called Shiny and how it can be used to communicate research findings in an interactive way. So a little bit about me. My name is Christina and I'm a data scientist on the Data Science Development Program at LIDA, which is Leeds Institute for Data Analytics. Before I came to LIDA, I studied mathematics and music at the University of Leeds. And my first and second 6-month project on the development program was related to geographical information science and urban analytics, which I used R to analyze in both projects. So R Shiny is a package to make interactive web applications, and it uses reactive programming, which means as opposed to a static report or paper, they usually.
It's still not working online.
Okay.
And I don't really understand why.
Sarah.
So. Yeah, so it's,
What was the issue?
I think, I'm
You
not,
share screen after you set the presentation. Right. So
so,
select there now.
that one,
yeah.
no, it's that one.
Yeah, that's the current slide.
So click that one for us, Sarah.
Yeah,
And then what we want to do is click, go back like that. That's to start your slides.
Yeah.
Is that okay? Is that something?
Yeah.
To do your shiny up there, you just want to change the window to your app.
Yeah, good.
Okay.
Okay.
Brilliant. Try again.
Okay. So I think I can jump right to the R shiny slide and so it uses reactive programming, which means that as opposed to static output, there is R running in the background, and user can play with the widgets and the plots and the maps update in real time. It also has configurable layouts, which means that there is no need to know HTML or CSS or JavaScript, which would otherwise be quite key languages to understand web application development. But these are predefined and have several options to choose from. And one thing to consider with RShiny that R must be somewhere. So that's either locally on the computer. So the user has R Studio or something that R can run on their computer, or otherwise it needs to be hosted online on a server, which is the ideal way. So then anyone with a link can go to the app. But the servers have both paid and free options, so that's something to consider when developing an application, to think how much memory or how many users or how many hours the application will need of runtime. So another package that I wanted to pay attention to is a package that creates packaged applications, and it's called Golem, and it's a series of tools to develop Shiny applications. So these help in creating scripts and creating structures for the applications, which help a lot to create something that other users can understand the code of. So the data I use comes from the first 6-month project I did with Professor Nick Mallison and Lex Comber from School of Geography, and it's Urban Transport Modeling for Sustainable Wellbeing in Hanoi. And in this project, I created a dashboard to communicate the survey findings. So I took the data of this household survey and I randomized each column so that the individual rows cannot be identified, and the data is publicly available on GitHub to play with. And the widgets include select input, checkboxes, and slider inputs, which then update the plots. And the most useful resource out of this page is the GitHub repository, as the README file there has all the other links. These include the Shiny Learning resources from the RStudio website, which is the best place to start with Shiny, as it has many blogs from the beginner to advanced level. And even when I checked it after 6 months, a couple days ago, it had many more resources than a couple months ago. So it's really a great place to start with a lot of exercises. Another is Mastering Shiny book by Hadley Wickham, which is fully online. And that lists how to create the application, how to create the inputs, how the user interface communicates with the server. And the internet production grade Shiny apps doesn't explain how to create these interactive plots, but it explains how to structure the code and how to create application that lasts. And these 3 resources, the package documentation, the video demonstration, and the publicly available book, are great sources of information about Golem. So I will now just share the dashboard. which is also on GitHub and can be downloaded from GitHub to be looked at the scripts and played with. So it has 3 tabs. The select input example, which is together and play your buttons team up. So in the first example, it shows the travel time of trips that were recorded in the survey of different occupations, such as work, direct investment, or private or student. The plots look almost identical because the data was randomized. The second example shows several widgets working together. So all 3 of these widgets, the select input, checkboxes, and the slider input, react to the same plot. So the first one filters which vehicle is there. And the second one is whether the box plots are shown or not. So this question was how many vehicles each household owns of each kind of vehicle. And the third one filters the distance to public transport. So we can see whether for shorter distances to public transport, there is any significant difference between households that own more of the selected type of vehicle or less. And this dashboard, it's an example where I used the visualization technique. In the real study, we used also models and widgets to play with that. But I decided to just stick with the data because the principles of using the widgets are the same. And the third tab, it will load in a few seconds. It shows 2 theme maps. And these are 2 color flat maps that shows the counts of origins and destinations that were recorded in the trips in the survey. And this can be filtered by mode of transport. So we can see which communes have the most origins and destinations of each mode of transport, which is a useful way to visualize and examine the survey data. So that's all for me. And finally, this is the link to the GitHub repo, which can be taken from GitHub and examined in detail. That's all from me, and thank you very much for your attention.
Thank you very much. So we're going to do questions at the end. Is that okay?
I'll just leave it there.
Is that, yeah, I'm sure I'll do something terrible with it. Is it okay to close your GitHub
Yeah. Well,
thing? We're not going to need, I don't really want to close people's slides because, okay. I'll close that one. Uh-oh.
That's fine.
Okay, that's all right. Okay, now it is my great pleasure to introduce Eric, who has a live demo. So I can't mess up at all, can I, Eric? It's not going to
You'll find a way.
Okay, now let's have a look at, so is that when you,
So I'll share my end.
you sharing from your,
Yeah, so oh, double sharing.
wait a sec, I might be able to,
Just have conscious security. And yeah, all participants to share screen. Yes. So we do that. Good, then we can come share this. Yes.
okay,
Yeah.
are you set to go now?
Yeah, I've searched.
Okay, John will tell us if there's anything wrong online.
No, everything is okay at this point.
You're a superstar. Go for it. Thank you, Eric.
Thank you, thank you.
So yeah.
Yep. Thank you so much. Yes. So hello everyone, and welcome to my presentation. So funny thing when I was coming, so I asked me, why I chose such a topic for my yeah. So it's essentially they're asking, does that mean people will still cry in data science? I was like, hopefully tears of joy. So let's see how that goes. So my name is Eric Panjao. I am a data scientist at the leader development data scientist program. Yeah, that's what it's called. My lovely colleague Christina, who just presented, is my colleague. So today we'll be talking about how Docker can simplify your work as a data scientist. This is basically based off on a talk that was held here some hours ago on Docker. So it's just a build up to that. So yeah, so I'll start with, I want to take you through something that I went through and how Docker helped us, especially our team. So this is our team who are dealing with urban transport. We're doing for sustainable in Hanoi, just presented by Christina. And this project, I was creating spatial and machine learning models to understand why Hanoi has a large uptake in the use of motorbikes. So that is what I was doing, led by Professor Nick Mollison, Alexis Comba, and my lovely colleague Christina Brankova. So this was at the end when we were winding up and we were very happy, probably crying tears of joy when everything was good and working. So, but I really wanted to take you a step back, probably at some few months before this. And this is how we were feeling, you know, very frustrated, especially at the middle of the project, where everyone has a glimpse of the data and the methodology, and everyone wants to share their, you know, everyone to share their code, and I want to build on another person's code, and I want to help my friend to bug their code. This is what it felt like for some reason, you know, very frustrated and just want to throw your PC off. So let me tell you the reasons why we felt this. So so some of these reasons you've gone through them. Some of these challenges you've gone through them. And the first one is this, where you know you tell people you've done the work, but it only runs on your machine and not any other person's machine. So probably everyone here has experienced this. So the next reason we were feeling that was so your code works, yes, but it has updated or downgraded another person's package, and their code doesn't work anymore, and you don't know what to say about that. So that's the second reason. That reason is that you're running on a different OS. You can't help your friend debug their code because you don't know anything about that operating system. It becomes a pain. Just we want to help, but you don't know how to deal with let's say the operating systems or the runtimes. Finally, you've created a model, but the model is big. You want to put it on Christina's dashboard, but yeah, it makes the dashboard lag. And a good thing would be to probably deploy the model on cloud and make just an API call. So these are some of the problems that we faced, and I thought to make everyone laugh aside, but these are some of the problems we faced. But we could I could summarize them into these three main things. One is the issue of reproducibility, where you want to take a snapshot of, you know, when everything was running, when version of the packages, let's say the data at that point, you just want a good snapshot when everything was running, and that when you can come back like 6 months later, it will still run, and your friend can reproduce the results, and also you can reproduce the results. The second thing was isolation, where you want a data science environment where that does not interfere with your existing pre-existing setup. So you want something that's isolated from your setup. Next is portability. You want to have your data science environment on your own, but also you can give your friend running on Linux or Mac OS or Windows or probably on Azure or these cloud services, and it still works for them. So how did we solve these challenges? We use something known as dev containers, and dev containers are just Docker containers configured to provide a full feature development environment. So they just build on top of the concepts of Docker containers. So we probably didn't attend the talk that about Docker containers. They can be just described as these isolated sandboxes that can compile your code and your runtime so that each Docker container becomes its own full-featured, let's say PC. It can run on its own. So how do dev containers, help us, extend Docker containers to have a full-featured development environment? So what does this mean in the perspective of a data scientist? So one, as a data scientist, you want an environment, or one as a data scientist or in a data scientist team, you want an environment where you have all the tools and runtimes that your teammates may need, so that if you do an analysis in R or Python or Julia, your fellow data scientists can reproduce the results without much pain. The second thing is that as a data scientist, you want control your ID, the ID you're most comfortable with, probably could be VS Code or RStudio. So these are some of the features that I'm talking about, how dev containers make Docker containers full feature development environment. So next issue is portability. As I said, being able to run your code, your environment on various hardwares and also container hosts in the cloud. And finally, same experience for every user, such that if my code if my code is running on this version of R, the other person will also have the same version of R or same version of Python and can get the same result. So same user experience for everyone. So no, people are not getting different results based on different software. So let's set our dev container up. So we'll be setting a dev container that has R and Python in VS Code and RStudio, such that this can be, we can link this to our data science team, such that the whole data science team has the dev container that has all this and can make things such as collaboration and portability and reproducibility that we talked about easy. So what do we need? So the first thing we need is a Docker file. So a Docker file, we can think of a set of instructions that instruct how to build that Docker container. So, and these are simply the main parts that you need figured out. So the first part is the base environment where your Docker file will build on. So the good thing about this is that there are lots of Docker files available out there, and there are teams that work day and night to make sure that each technology has its own Docker file. So for instance, here I'm launching, when I'm building the container, I launch a Docker file from the Rocker project. So the Rocker project is a project in the R community that ensures that there are Docker containers for R. So you use the from command to to instantiate a base environment. So once you do that, building Docker allows you to do it in layers. Then you can add some layers using the run command. So the run command just used to change the base environment. And for this, we're using run command to install some Python packages and some R packages. So these are probably instances where you are already familiar with, or installing pandas or Seaborn in Python and R packages such as Palmer Penguins or Shiny model. So this is the first thing you need to set up a dev container. So this is a Docker file. The next thing the next and the last thing is the dev container.json. So what is this? So a dev container.json just describes how you enrich your Docker container that we just, your Docker file that we just described earlier to fit a development environment. And this can mean configuring how your VS Code will be very similar for everyone that is using your dev container. For instance, you start off by building with the name of the dev container. This is very trivial, but we point it to the Docker file that we just explained earlier. And then the next step, if you're familiar with VS Code, this is where you just define the extensions that are required that everyone who is working with the Docker container can require or would need to work with the runtimes or languages that you've set up your dev container to use. So these are the two main things that you need. And to show you this in action, I'll show you this up and running. And just allow me to share my screen again, where just a minute. So allow me to just share my screen where I take you to, yeah. So here I'm taking you to so this is a virtual PC. I don't have R or Python or anything installed, but I've already set up the dev container that I just described, which has R and Python and VS Code and everything. So how will we launch this? So we'll just have to launch up our VS Code and come in here and say, so want to open a folder, the folder that has the dev container. So this is the folder that I'm just opening here. So ResCompLeeds. So, and in this folder just contains the dev container I described, as you can see with the Docker file where we're installing some packages of R and Python, and the dev container.json. So this is what you would share with your team, and the team would just come and reopen it in a Docker container. And in this dev container, you don't have to have anything installed. You don't have to have R or Python or Julia. You just have to open it in a container instance and get up and running as soon as possible. So this is taking up some bit, but here we go. So as I said, I don't have R, I don't have Python, but I have set up that dev container just described. And as a data scientist, I can come and explore some penguins. Let's say explore data where everything is set up. I just need to define the kernel I want. So it has Python, it has R, things that that I just talked about. And this allows anyone, and this allows you, the data scientist, to have a reproducible environment where you can share this, has everything installed, has all the data installed, has particular packages and their versions, the ones that you defined, and working with this across your data science teams becomes easier because no one will have different versions of the same packages or different versions of the same language, and everyone will be getting the same results. So this is this is the beauty of dev containers in a data science perspective. So that is how we'd run a Python demo in VS Code and in using notebooks, as you see. So just wrapping up, I really want to show you how easy it is to modify it if you want to say you want to use the RStudio IDE. So what you just do is you go again to the dev container. Dev container.json, the one that I described, is used to modify the container to make it a developer environment. And you just have to specify some few parameters. For instance, I know that that rocker comes with some certain ports, so I can just add some parameters that say expose a port from inside the dev container and make it available locally, and then specify some parameters such as do you want the port to open automatically or not? And then lastly, say when you create the container, fire up the RStudio IDE. And yeah, so with this, you can have a fully featured development environment that is reproducible, that is portable, and hopefully allows everyone to do their analysis in a synchronized way. So this will be the end of my talk because I see time is running out. But maybe you're wondering what if I want to build a dev container with C, C++, or Julia or Java or friends. So as I said, there are teams out there that are ensuring that we have dev containers, or you don't have to know a lot of stuff. You can just come in and have a small running. You have code to get you up and running, and that's why you can find some more information on how to set those up. So just wrapping up, dev containers are good for your data science workflow because they're reproducible and customizable development environments. We created one that has R, Python, Jupyter notebooks, RStudio. It can create isolated environments that will change with pre-existing setups, portable on both macOS, Linux, or Windows. It's great for workshops, and hopefully you'll be crying tears of joy. So thank you, and here's the repo with the slides, with the link, with the dev container, and if you have so just a minute. And if you have a GitHub code Spaces, so this is a GitHub on the cloud. You can also run this up. You can spin one up and get the same experience that I got when I was doing in the virtual computer. So thanks a lot and for listening, and hopefully you can take Docker and you can take dev containers and make them extensible, portable, and make your data science more of tears of joy. So thanks so much for listening, and take care of yourself.
Okay. So, do we have questions for any of the three speakers? So remember, we have, just to jog your memory, we have Amani, who talked about the use of language in Arabic. We had Christina, who is talking about shiny things in R, and we've just had Eric, who's talking about Docker. So do we have any questions? No, there was a cancellation. Oh, is there? Oh, we've got Adam. Oh, Adam, I hey, come on, sorry. I'm so sorry. Thank you, Graham. I'm lucky somebody's right, okay, now so let's look. Oh yes, look, there you go. God, lucky somebody's paying attention to that. Right, now what was it you said?
Present it first.
Present it first.
See full screen.
Okay.
Go back to your
I don't know if I can get a Zoom.
press start. Or press Windows key. There on top.
Okay.
Sign on there, and then click your Zoom window.
Oh yeah, here we go. So the other one, and we want to share screen. That one.
Okay.
Cool. Let's see. Thank you, Adam. I'm sorry about almost not knowing that you were here. Good luck.
Well, I'm Adam, here to talk about the Lead Analytics Secure Environment for Research. We call it LASER. I work upstairs with the data analytics team in Leader. So LASER is a secure environment for research. It's built on Azure. I did have some notes on the slides. I don't know if I'm able to see those. No, right. So I'll have to just try and it's built on Azure. It's maintained by University of Leeds IT Services, supported by the data analytics team as Leader. It effectively, in its simplest form, a virtual research environment sits on LASER. It's its own resource group that has some project storage and a virtual machine. We can remote into the virtual machine and access that project storage. There will be more than one virtual machine for concurrent users. You can scale the virtual machines up and down to increase, decrease processing potential. And it's all network segregated. So there's no internet access from inside a virtual research environment, or VRE, we'll start calling it. There's really high controlled data flows. You can't copy and paste to and from a VRE. At the moment, all data transfers are facilitated by the data. And those controls have enabled us to comply with various security frameworks, such as ISO 27001 and NHS Digital Security Protection Toolkit. Those assurances have allowed us to process really quite sensitive data that otherwise wouldn't be made available for research. That could be personally identifiable, commercially sensitive, or just other special category. that's laser. That's kind of what it is. The benefits of laser. Laser isn't our first secure environment. We have had previous attempts with the IRC. The IRC was built on premise, whereas laser being in Azure is an improvement, frankly, because it's scalable. It's like as big as Azure can be, laser can be. So we've got an increased capacity and performance. It's, you know, like I said earlier, you can add VMs to a VRE to increase the number of users that can access that shared secure storage. And you can scale up and down the VMs. And you can have more than just VMs. You can add any Azure native resource. The most common at the moment is databases, PaaS databases. But there's, you know, any number of things that if Azure offers it, it can be included within your VRE. Cognitive services is something that we're looking at providing in the near future. Researchers have increased control over that environment, and again, the security assurances allow them to work with data owners to provide, you know, to provide those assurances that their data is safe with us in a research environment, and those data providers can then are more willing to release data that they perhaps wouldn't otherwise be. We've got access to anything that can be installed. Currently just on Windows. We don't have Linux machines just yet, but that's hopefully coming in the future. So anything that can be installed to Windows can be installed to your VRE. Compliance security, we've got a dashboard so you can monitor the costs and the usage, control when your VMs are on and off, and all that good stuff. So yeah, like I say, laser is designed for, well, it's built in Azure and can leverage increased computation. Is that a warning? It's just a big it is designed for as a secure environment for sensitive data. So if you don't have sensitive data, the recommendation would be to go somewhere else where those controls won't apply, won't restrict your research unnecessarily. So the sensitive data that laser has been designed to enable research on, we operate a risk classification tiering system. It's based on the one developed by the Alan Turing Institute. There's 5 tiers going from tier 0 to tier 4. Tier 0 is, you know, you'd read it on the back of a box or a crisp packet, and tier 4 is, you know, GP records and kind of individual sales data from a retail. The real sort of top tier personally identifiable stuff. And laser has been designed to accommodate research on tiers 3 and 4, so those top 2 tiers. Anything below that can use University of Leeds other platforms, which there are several and many. But the tiers 3 and 4 can be used in the laser, and we've got quite a granular application of technical controls to VREs, depending on the sensitivity of that data. So, for example, tier 3 VREs that host tier 3 data can be remotely accessed, whereas VREs that host the more sensitive tier 4 data are restricted to only be accessed from safe rooms within the leader offices upstairs. So there's those additional physical access controls as well as the technical. Yes, which I shouldn't have mentioned until this slide comes on. So brief guide as to how it works. It is quite simple, and you'll be familiar with it already probably, just through using Windows computers. We'll focus on tier 3 VREs that can be remotely accessed, but it's basically the same with the safe rooms as well. So you navigate to a URL, And say, for instance, a thin client that can only see that URL, so there's no bother there. Then you log into the Citrix storefront, which presents each virtual machine that you've got access to. Like I mentioned earlier, VREs can have more than one virtual machine, and they'll all appear here. So you pick one you want to log into, and it boots up, and you boot it into a remote Windows 10 virtual machine, from which you can see the project storage and any other resources that are available within that VRE. VRE is just a resource group, to all intents and purposes. And you can access Software Center, which is the vector for software installation within VREs. And we've got lots and lots of software currently available. For if you need something that's not currently available through Software Center, you can get in touch with us. We work with IT services to make it available through Software Center, but it's just that that additional bit of security with the software provision, so that you can't install any old thing. Even though it's network segregated, it could still, there's a risk. There's a risk vector there. So Software Center kind of helps to mitigate that. And when it works beautifully, and it normally works. We also have the Azure portal. If you've done any work in Azure, you'll be familiar, where you can see all the resources for any VREs that you have access to. You can control them to a degree. So VMs, if you've sat down at a table at home and had that funny feeling that you've left the oven on, you've left the VM running, you can just quickly log onto Portal and check, and you can stop it if you have, because costs can. Those costs, and they will keep ticking up. And here, talking costs, you can monitor what your VRE is costing. And there's lots of ways to drill down and dice and slice this data that Portal offers. It's dead useful. It's probably not used enough, but it is dead useful. And here you can pretty much ignore the numbers, but it gives an illustrative kind of idea of costs. And just the fact that larger VMs cost more than smaller VMs. Using them more often and more frequently, it costs more than not. So use it a lot, it costs more than using it not a lot. More storage costs more than less storage. It's that kind of. So we can tailor the VRE to your budget. If you've got this much money, just use it this much, or we can tailor it to your research needs. Whatever is the bottleneck, we can make a large or small VRE depending on your requirements. It's just an example of a costing that we'd send out to the researchers as part of our research management process on the DATs. So we would. Do I go into it? Yes, here we go. So within the DATs, we have within Leader, we have a research management process where we can help researchers end-to-end life cycle of their project. From I've got an idea for a grant proposal, but I need to write a budget line to know how much money we're asking for. We can help design the project, design any, check if laser is applicable or appropriate for your project, how much it might cost to get something, and help with that grant application, all the way through to building the research environment, using the research environment, and then closing it down at the end and making sure there's a secure destruction of any data that needs to be destroyed. Or we call it archive, but it's not really an archive service because it's relatively short term. Some projects, some researchers have like regulatory requirements to hold the data for a number of years after the project closes. So we can do that in Laser and keep it within a secure environment and segregate it off from all the networks. Again, at cost, but it's much reduced for, you know, periods of 5, 10. I think we've got something coming for 30 years. See how that goes. But at the end of which, you know, because it does cost each month, there's a cost, so it's not really indefinite. But yeah, that's a research management process. Will help guide the researchers through all of that. We have a website. There it is. If you want more information, it's not just on what laser is, but also what the data are, how we can help with things, and how you can use laser if you're already on it. Lots of useful user guides. Thank you.
Well, I'm glad we didn't miss that. It's really interesting. Thank you. So now we are definitely taking questions. So again, I'm going to remind you, we had Amani who talked about language, different use of connectors in Arabic. We had Christina talking about Shiny. We had Eric talking about Docker. And we've just had Adam talking about laser. So what questions do we have for everybody? Go for it, Graham.
One's fresh in my mind, and Adam's just been speaking. Adam, lovely secure environment. I think the slide you went over quite quickly. I think on the right had something about the team help you get stuff in. You don't just do it yourself. I'm wondering, you get towards the end of your project, you're going to write all your papers. You want to export the non-sensitive, but high-level aggregations or summaries or analyses. How do you get stuff out again if it's also secure?
That's us.
Okay,
At the moment,
again, it's a service.
it's part of the service, yeah. So we would perform those disclosure reviews, check against that share agreements, make sure that you're not trying to explore anything so sensitive. I think we just do directly platform that you can just log into and download those files from. That's at the moment. Now we have been working. So I'm glad you've asked. We have been working on a data transfer app, so that some of that responsibility can be delegated down to the researchers for those less sensitive projects, the tier 3, where because a part of the information security policy that applies to that is that transfers to and from the security license are often that's registers. So we've been developing a data transfer app that automates that side of the process. Lot of requests to import the process is actually put the app. Log those requests in the PI or the responsible party of that. The ability to run those checks themselves and approve all of the checks. Those requests for requires so that we can delegate that to the research teams.
Paul, you see?
What are those covenants that you put software on there at the moment?
At the moment, I mean, without that. Without that, RFI. And we're able to use those within laser quite seamlessly, actually, because I know they work best with internet. With the IRC, we really struggle with that lack of internet connectivity in those now we've got this middleware that sits just on the threshold of laser architecture that allows the researchers to configure those environments to kind of build into that middleware and put it down.
Okay, so before we go, are there any questions for the other speakers? Anyone have any questions for the other speakers? Okay, I'll do a quick fire one for each speaker, if that's all right. So, Amani, one of the things that I was interested in is, so the applications of your work, does it help people who our language teachers teach students? Was that the sort of aim of the analysis you were doing?
Yeah, so really after, I don't know if you mean like, it's really like this, you know, like some changes.
Yeah, I'm just
Oh, you
sort of
mean-
thinking about the
Okay.
overall, aim of your research. Does it help sort of language teachers?
Yeah, language teachers and also material, anyone who's involved in doing the materials for,
So hi everyone, welcome to this session. First up, we have Dodi, is that right? No, Allah, sorry, we have Allah. This is a recorded talk. I will just get that up.
Hello, everybody. I am Ala Al-Sakir. Thanks for having me in this nice conference. I am a PhD student at University of Leeds and a lecturer at King Faisal University. I'm going to present a comparative analysis of weaker RapidMiner, and this is part of my PhD work, which is still going on research. It's under the supervision of my great supervisor, Professor Eric and Dr. Duana. To start with outlines, I would go to give you an introduction of data mining and text analytics, and then an overview of tool kits that called weaker RapidMiner. I will show you an experiment of text analysis to cover these 6 points. So let's start with data mining, which is mainly concentrated on discovering knowledge from huge amount of data. We can see data around us everywhere, in emails, in websites, text messages, in social medias such as Twitter, Facebook, and Instagram. It has different types, for example, text, sounds, and images. In order to get a knowledge from this data, we have to apply some machine learning methods, such as classification, clustering, or association. And one type of data mining that concentrates more in dealing with text dataset is called text analysis. And in case of we have big data, we call it text analytics. So in case we have this example, if someone asks you to add 2 of these numbers, 5 plus 2, you may think a second and give the answer, which is 7, right? Suppose you have this equation, Pythagoras. You may need a pen and paper to calculate it. So it may take more time than think about it in your brain. How about if you have complex equation? You may need to use a calculator, right? To help you to do it in faster and easiest way. Similarly, for text analysis, we need a tool that helps us to do it in faster and easiest way, especially for non-programmers, that they don't need to write any single code to do that. And one part of text analytics is called sentiment analysis or text classification, where we classify the text based on the meaning of the text. And because the text is not understandable by a machine, so we have to convert it first into word vectors or numbers to be readable by machine learning. Here we have weaker RapidMiner as considered as top of toolkits that use for machine learning algorithms. To start with weaker, it stands for Wikato Environment for Knowledge Analysis. It's built by a University of Wikato in New Zealand. It's an open source Java toolkit, so it's free to download and use it for data mining and text analytics. It's widely used in universities for learning and teaching, and also for practical applications in industry, because it has many machine learning algorithms built in, and it is easy to be used. It's really powerful in classification models. Moving up to RapidMiner, it's as well open source Java toolkits used for data mining, and it's provided by University of Dortmund in Germany. It's useful for AI and researcher because it has very friendly user graphical interface. It's very strong and powerful in predictive analytics. To compare these toolkits, we will go over these 6 points or criteria by describing the use case for text analytics. We'll start with interface design for each one, and then go forward to see the dataset format accepted by each toolkit and the pre-processing need to be applied. We will visualize some statistics, and we will see which classification model is suitable for this case, and then we will present the evaluation or results. So this is the interface for Weka. We can see here the classes tab, and also we can see here some statistical information and some dataset attributes. For the dataset format, it's currently accepted ARFF and CSV, and there is other format, but if you have, for example, an Excel sheet dataset, you have to convert it to either these types to be used and readable from Weka. In this use case, the Twitter sentiment analysis is used, and it has 3 classes: positive, negative, and neutral. To clean the data and pre-process it, we apply some filters as unsupervised filters, which is Twitter to lexicon feature vector to count how many positive words in each tweet. And other filters are applied, which is we can allow us to do that, to apply multiple features, which is really good. And in each one, we can adjust the lowercase, tokenizer, steaming, word engrams, for example, here one, to make sure that it will separate each word from the text. All these pre-processing to prepare the data to be suitable for the model. So for the statistical information that we can see here about our data, we have 3 attributes. We don't have any missing values, the type of the data attribute that we selected, and here we have some counts of how many tweets in each class. And here is some visualization chart to show the differences. We can visualize it in advanced way by selecting here, for example, 3D visualization. For the classification model, support vector machine is used as a linear machine learning package. It's suitable for tweets classes, as we have here, positive, neutral, and negative. And we can adjust here all these numbers or values. We can allow us to download and install more other packages, for example, from the package manager. And for example, in this use case, I downloaded the lib support vector machine and effective tweets. To see the evaluation result, the percentage split is applied to separate the training and testing part, for 66% for training and the remaining for testing. And cross-validation could be used, but percentage split is faster here. And we can see here the accuracy is 64%. And also we have the coefficient metrics and other information such as the time spent for building the model and the time for testing as well. You can adjust all these information from selecting what you want to present. To move up now to the rapid miner. Similarly, it has a useful interface. And when you apply some process, it will look like this way. To start with data formats, all these data types are acceptable and can be readable by RapidMiner. In this use case, here we have sentiment analysis of 200 movie reviews. all these two examples presented today is from existing examples from the toolkits itself. In this example, here we have two classes, positive and negative. The pre-processing applied and filtered set rule to consider the target attribute as a label and to convert the data from nominal to text. And other pre-processing and filtered such as tokenizer, transform cases to lowercase, and filter stop word to make sure that each word is separate from the text. Some statistical information and visualization charts could be seen from the result tab. Here we can see how many negative and positive classes, and we can see here the data type and we have some missing values or not. The classification module similarly here applies support vector machine. And for the related packages could have more models from the text processing extension. For evaluation part, the cross-validation process have been applied, and to measure the performance, we have here the accuracy is 63%, and we will have also all the information for the coefficient matrix. After now, we're done from this comparative analysis, you may think, which one is suitable for you? If you have some data and you want to analyze it, will you going to use Weka or RapidMiner? You may think about it twice. You think about your data type, the model that you want to use, and the purpose, why, and what you want to do. As we said, Weka is very powerful in classification and RapidMiner in predicting. And also put in your mind that RapidMiner has limitation for the records. It's with 10,000 records, while Weka can deal with more big data. So think about it twice before you select what you know. Thank you again for your listening. Hope you enjoy it. If you have any question, you are welcome to contact me through my email. Thank you.
Yes, of course. Yeah. Okay. Hold this up.
Okay. Thank you. Okay, good afternoon, everyone. Today I will talk a bit about simple tool, but quite powerful, especially for my research. So I will talk about message pack, and this is belongs to Z standard, actually, Z standard compressions. So this is a compression tool for data sets I use in my neural network training. So no,
Oh, if you click on the slide, then
okay.
yeah, then try it.
Okay. So my name is Jody Dharma from School of Computing. Currently, I'm doing research in 3D realistics and interactive fluid and deformable solids simulations using deep learning. So specifically, right now, I'm doing some prediction for text ring affections using neural network. So basically, we may save maybe our data into there's kind of text file. For example, some people say JSON or CSV, and especially for me, usually I export my data from other tools, for example, from Houdini. I set my point cloud into PLY files, which is actually a text file, but this is easy. Easy to read, and then we can also inspect directly to Notepad or something whether the file is written correctly or not. But the problem is because this is text file, as you know, when we have a huge number of these files, the storage become required much bigger and bigger. So we need large space in our disk. So it is easy to read, but not efficient in terms of space. And another thing as well, because when we save in certain format, we need also parsing time, because we read a text file and we need to interpret based on the structure. So it's also require time to read. Especially when you do deep learning training, usually we do multiple experiments. Sometimes we repeat the same experiment again and again. So the total accumulations of the reading time become large and large. So it will affect the overall experiment durations. Another thing as well, if we want to, for example, we want to train a network, and we want to pump the network with large number of scenes, for example, and each scene has a lot of particles, for example. Sometimes we need to read large file in one batch. So when we save this data in text format, it also becomes not efficient, especially when we read on the fly on training sessions. We need to pump the data into GPU, but the reading process becomes the bottleneck. So this is another issue. Another thing as well, when we publish our code for our project, how the data become has a high reusability. Maybe we use the same data set for different projects. So when we have a data that has good portability, so this data can be used in different platforms. For example, Python, JavaScript, or another framework or programming language. So this is one study case in my experiment. So I have a lot of scenes of cortex affection. So this is just one illustration. So for example, here, this is the smallest number of particles in one scene that I treated. Actually, I have also another training data using 100,000 particles. So for example, here we use only 15K particles, which has ID, positions, and velocity. And then just a snapshot of a frame of simulations will require 1.5 megabytes per file. So when a scene has, for example, here I have 1024 frame to capture the sections of the cortex, for example, it will generate 1.5 gigabyte just per scene. And in supervised learning, we require a lot of scenes usually, sometimes hundreds or thousands scenes. So only just 25 scenes will consume 40 gigabyte size on this. and 100 scenes will 150 gigabytes. Yeah. So what about 1000 scenes? It's almost 1.5 terabytes, yeah, just for storing the data sets. So even the OneDrive will also fulfilled by this data. So how we store the same quality of data, but just consume much small space, a smaller space. So actually we can easily just compress this when we're using zip or other kind of formats, yeah, like we used before. But what we want is not just in terms of storing reducing the space, but we want also while reducing the space without sacrificing the reading speed. So what we do here, we transform the data into a binary format. So the same data, like in JSON or in associative array in NumPy, for example, but we store it in binary format. We use it a tool called message pack. Yeah. So, and after we convert I will store the data into binary, and then we extend the compression using the real-time compression tools called Z-Standard. This is, I think, published by Facebook. So this is a very good compressor, not just has a good compression ratio, but also has a very high speed extracting time file. So for example, here I just 43.9 gigabytes, almost 40 gigabytes. So after transform the data into message pack and then continuing with compression with Z-Standard with level of compression 22, I got a file just 9.41 gigabytes. So we save 7-8% space using. So what is message pack? So actually this is like JSON, but fast and small. So we store the same data, but in very compact formatting. So it's kind of like serialization actually, but we save a certain chunk of data. So, and this message pack also supported by over 50 programming language. Yeah, also in Arduino and other platform. So the difference is this is the binary, and writing and reading is much faster. Yeah. So so let's say we don't compress the message pack, just write it as a message pack and read it. So we get a small file and also very fast because it's binary. And then we extend with Z-Standard. So this Z-Standard actually a fast compression algorithm. So providing high compression ratio. I'll show you here why this is very fast. So this is the relationship between compression speed and the compression ratio. So we see here when we increase the compression ratio, and then the compression speed will lower linearly. So it's the complexity is linear. So compared with other compression algorithm, for example, we see here the time will rise exponentially. So that's why they call it real time, because the compression complexity is linear. So how could we use this message pack? It's very simple actually. So for example, here we have an array of a list of 1, 2, 3, and then we just call the message pack.pack b, and then passing the data, and then we'll convert to binary format. This is just parameter for compatibility with the previous version of message pack. So this is I give an illustration of in case of fluid simulation. So for example, here I have in NumPy, for example, I have data, position, velocity, and mass, for example, and then I have 1,000 frames. So I just store the data into tuple here, position, velocity, and then store all the list. So this is like a column. Yeah. So I'll store the points and velocity, and then put them in one associative array, and then call it the compression message bank. So this is the implementation of the function. So you see here, we just call the import the Z standard library and then the message bank. This is implementation in Python. So for, we just as the inner parameter here, we just pack the data that we generate here, and then the return of the return value of the message bank we pass it to the Z standard compressor. Here I use the highest standard compression ratio level 22. So we could get the smallest level possible. And then later, when you want to read the data, and so you first okay, just what causes them. Okay, so and then just one more thing important. How, because we know that in GPU we have a limited space of memory. So how do we load the compressed data in real time? So we can divide the compression data, for example, from 1,000 frames, we divide into 16 batch, and each batch has 60 frames. So we just extend the iter, so the iterator in Python. So when we do the training, we just, for example, here when I do the so when we do read the data, we define the batch size. For example, here we have 16 batch size, and then every time the GPU read the data, it will read each chunk of the batch. So it will read 16 times of the compressed data, which is already divided into 16 parts. And then, because it's a binary, it can pass it directly to the GPU memory and easy to read. So that's the thing. Because the time is up, that's the thing I want to say. Thank you very much for your attention.
So next up we have Sudha. I think that's not your name correctly. Yeah.
You need to reach out that way.
Do I need to?
Yeah.
Oh.
Did you click on that?
Did I click?
There's how many blocks there?
Oh, it's yesterday.
Reappear.
Right, thanks. Right. This one is the evidence.
You need to, because it's been silly before, right? You need to present first. And
It didn't let me press the button.
Well, didn't it?
No.
Before, right? You share the wrong screen.
Hi everyone, my name is Sudha. I'm a PhD student in Assistive Group School of Computer, and my research is supervised by Dr. Ali Guya and Professor Alex Frangi. The title of my talk today is about generative modeling for shapes as a graph without correspondence using the graph convolutional neural networks and attention modules. First of all, I will present an introduction about the importance of human shapes anatomy, and the importance of shape generation, and I will talk about all challenges here. Yes. Then I will talk about the object of my research, and we will talk about the details of the proposed method, all the experiments and discussion, and I will conclude the talk at the end. First of all, I want to answer the question why organ shapes anatomy is important. Shape representation of human organs actually has a various application in computer-assisted diagnosis, treatment planning, visual explanation, and also be a useful tools for medical training. But another question is why shape generation matters. As all we know these days, artificial intelligence is a critical technology for a foundation of any healthcare systems. Actually, we need a publication of real patient data to train the generative model and generate shape. But the point is there is a challenge here. The challenge is a lack of availability of real patient data, but it seems that shape generation or synthetic shape generation could be a possible solution here. A big application here is about in silico materials. Actually, using this shape generation models, we can create a virtual cohort of patient data to optimize and assist our medical devices. In this slide, I'm going to talk about the shape representation. In all literature, shape can be represented as a volumetric data or point clouds or point sets. But there is a challenge between presenting the data as a point cloud or volumetric or surface shapes. Although the point cloud learning presents a remarkable results here, but there is a problem here. In point cloud learning, actually, the topology of shape is neglected, so the 3D shape modeling is not accurate enough. So we are motivated to represent our data structure as graphs. So with representing a graph, actually, I will say that graphs are kind of data structure. Is a non-Euclidean data structure models by vertices and edges. With presenting a shape as a graph, actually, not only we can learn spatial features from the nodes, but also we can learn surface features like smoothness, curvatures, via the edge information. Another topic here is about shape generation modeling or all the generative modeling. The systematic approach behind the generative modeling is about learning and estimating probabilistic distribution function and then sampling from that estimated PDF to generate the synthetic data. But there is a limitation in this generative modeling. First of all, in traditional generative models, I should say that they are not able to present certain properties like water tightness, especially for organs anatomy. And about the more recent generative models like VAE and GANs, they only can deal with the data with the same structural topology or fixed topology, and also they can generate only fixed topology structures. And also they need the data with correspondence between them. But all of us know that real world graphs actually doesn't have correspondence, because the topological structure are different. So we're going to deal with these two problems here in this research. First of all, is about variation of graph structure across the training data, and the second one is there is no meaningful correspondence in real data. So we target these challenges by presenting an unsupervised framework to learn a probabilistic generative model by presenting a shape as a graph and then establishing vertex-to-vertex correspondence between the graphs using the vertex embedding and attentions. Here is a short pipeline of our proposed method. Given a population of shapes like levers, we can see that all levers related to different patients has a different structures, means a different number of nodes and different adjacency matrix. So we will present attention map between each sample of training data and a template, and also our algorithm can learn an atlas shape for the whole population of data, and then we will find the correspondence between the shape or correspondent shape, and then we will use a generative model for synthetic data generation. In the next slide, I'm going to talk about our proposed method in details. Given a population of graphs with inconsistent structure, we present a GCN attention network, actually a graph convolutional neural network, a special one. Capture both local and global information of node embeddings and present vertex embedding Z, and then we initialize a template mesh and start the iterative process with considering an attention layer and computing the similarity between the vertex embedding of each sample of training and atlas mesh. And then we will find the correspondence or correspondence map between each sample of training and our refine atlas mesh. So after that, we will have a population of data with correspondence between all of them, and we also, our method also are able to learn atlas shape. So given the normalized population, we can use now a generator network like variational autoencoder to generate synthetic data, and the whole framework works with minimizing the loss function. So here is the evaluation of our work. First of all, I'm gonna say about evaluation of correspondence quality. The first method is about visualization assessment. So you can see that we can point some landmarks in Atlas, and the blue line shows the meaningful correspondence between each landmarks on Atlas and two cases A and B. And also, these two maps shows the correspondence map between each sample and Atlas. And as you can see, the important landmarks, like triangle one that shows lever generally, it's preserved in both samples. And here is another example on left ventricle data. And I also forgot to say that this color-coded vertices actually shows the posterior probability of meaningful correspondence between each landmark on an atlas and each vertices on cases or samples. Another evaluation about for correspondence quality is evaluating the quality of generated shapes. We actually compute generalization and a specificity metrics that you can see that we also consider tree distance metrics. You can see that our proposed method outperformed the CPD, which is a point cloud-based learning. And here is some results of regression. The first row shows the actual data with inconsistent structure, and the second row shows the color-coded error on the normalized structure. As you can see in the liver data set that we have only 140 number of training data, algorithm can still capture the variation over the population. And also we have better results in left ventricle data with a very low error on regression, because we also had 4,000 data for training in LV data set. And in terms of generalization, first of all, we selected the best model. Actually, high performance model is the model that marker is more closer to the corner, because we have less generalization error and less specificity error at the same time. The best model is L or latent dimension 16. And here is some ablation study between GCN attention VAE, GCN attention PCA, and CPD VAE. The score marks is related to GCN attention VAE. As you can see, the specificity error means in all panels tends to be in the left, means GCN attention models, GCN attention VAE models actually generate more realistic synthetic data. And here is about population statistic evaluation. Actually, with generating some synthetic data, this blue ones shows the histogram of synthetic population for LV and liver, and the red one, yellow one shows the real population of both data. As you can see that a model can generate realistic samples to distribution are similar, and the p-value is less than 1,000. But in liver dataset, because that liver dataset generally has more variability across the training data, and also we had less number of training, our generation model couldn't generate a wide variation. And here, yeah, it's the last one. And here is some visualization of synthetic samples for GCN attention VAE and PCA. You can see that the models in the first, the samples in the first row and the third one are realistic, more realistic. So as a conclusion, we proposed an unsupervised generative model using the presentation of shapes as a graph, and then we actually computed attention drive correspondence between each sample of training and an atlas shape, and then we normalized all the structures over the population, and then we can train a generative model to generate synthetic data. But there was two problems in our work that we're gonna target for our future research. First of all is we actually didn't refine the node embedding strategy yet, and we only consider one unique atlas shape. Thank you, everyone. If you have any questions.
Okay, so next up we have Rhiannon. Nice. Yeah, that's one. Nice to meet you.
Yeah. And then you should, no, don't go snake, because I get rid of it then.
Oh, right.
Yes, you should be able to go. You should be able to see the present.
Oh, yeah, that one. Yeah. No, I'll hold this up to 1 minute.
Right, so I'm Rhiannon and I'm here from the School of Food Science and Nutrition. I'm in the third year of my PhD. I'm going to present how I'm using the supercomputer to model kidney stone growth. So kidney stones, they affect around 10% of the global population. And main problem with them is they're recurrent. So once you get one stone, you're very, very likely to get another. And as many people with kidney stones know, they're extremely painful and they cost the US over $5 billion annually in treatment costs. So the way kidney stones are formed is that crystals form in the kidney and they attach to the kidney walls. And eventually, through treatment, they can be excreted out of the bladder here. And the most common compositions of kidney stones are from calcium oxalate, specifically monohydrate and calcium oxalate dihydrate. So you may be wondering, how on earth are you using a computer to model kidney stones? So the main problem with kidney stones is that we don't actually know what chemical interactions are causing them to form. So what we're trying to find out here is why stones are forming and what chemical interactions are occurring between this mineral, which is 97% of the kidney, and the 3% of the organic matrix, and whether these interactions could be stopped atomistically. So this is an image of 6 different types of kidney stone, 5 of which, A to E, are actually formed of the same mineral. And you can see here that they look vastly different. And that is potentially because of that 3% organic material that is within the stone. Now, this will obviously be very individual to each patient. There'll be lots of things in the urine, which won't be in other people's urine and vice versa. And this one at the end here is formed of a mixture between calcium oxalate dihydrate and calcium oxalate monohydrate. So this may look like a black hole, but it's actually the proximal convoluted tubercle of a rat kidney. So this is within the kidney, there are over 1 million different nephrons, and the nephrons are composed of different tubercles. This is one of them. And what you see here are these fibers, and these are responsible for the filtration of your sugars, your proteins, your salts from your urine back into your bloodstream. And this is where kidney stones are likely to form, where the crystals of a certain salt will be in such high concentration that they crystallize and precipitate. So there's 2 accepted models of why kidney stones can form. First, we have the free particle model, where there is so much precipitated crystal that it just becomes so crowded within the kidney, it then essentially blocks the tubule we saw before. And the second, where the tubule wall becomes damaged, and this causes crystals to adhere on the wall and agglomerate over time, growing the stone attached to the kidney wall. So this is an experimental image from literature of the inside of a kidney stone. And you can see here these dark and light layers. So each of these pairs of layers are about 140 nanometers. And the darker areas are the organic layers, with the brighter layers being the crystal layers. And what we're interested in here is seeing what is causing these organic and inorganic layers to bind, and whether it's the organic causing the mineral to bind and grow as we go forward. This is another image of a stone, a bit more zoomed out, and you can see different layers within the stone. So we have here the calcium oxalate monohydrate, which grows in these clear striations. But we also see these empty pores. So when these images are taken, the organic matter has degraded out of the kidney. When they're extracted, they obviously clean the stone and that degrades the organic material. So we have empty pores, which then calcium oxalate dihydrate crystals are then growing into, which is shown here. So in this work, we've used the first principles quantum mechanical code CASTEP. And what that does is it moves atoms into their lowest energy position. So we're focusing on atomistic chemistry between the crystals and the organic molecules. So we run these calculations on ARC4 over 120 cores. The geometry optimizations take about 48 hours, with the larger dynamic simulations, which I'll be showcasing here, which take over about 500 hours to complete. I reference absorption energies, and this is what we use to determine if something is favorable. So we use the energy of the system, and we minus this from the energy of the model surface that we've constructed, plus the energy of the molecule that we're looking at absorbing onto it. So we decided to focus on calcium oxalate dihydrate, as it's a prominent mineral in kidney stones. And we've specifically decided to focus on this 110 surface because it's the most observed surface within cod crystals on kidney stones. And we've modeled this with our model here on the right, which we geometry optimized on ARC. And this was our model surface for our calculations in this presentation. So we began to look at the phospholipid phosphocholine, and that's because phosphocholine is seen at elevated levels in stone sufferers' urine over healthy patients' urine. So what we did is we absorbed this onto the surface using ab initio molecular dynamics. And what we saw was that at first the phospholipid head group bound to the surface like this, and then it collapses onto the surface. And when this collapses onto the surface, it actually binds favorably to the surface at the bottom with -5 electron volts. However, when we do this with calcium oxalate, we actually get the calcium oxalate binding with -7 electron volts, which is more favorable than the phosphocholine. So that suggests that the phosphocholine probably won't bind to the surface in competition with the calcium oxalate. However, if it can't bind to the surface in competition with the calcium oxalate, if it bound to the surface when the calcium oxalate wasn't present, could it cause further calcium oxalate to grow onto the surface? So to model this, we've placed the calcium oxalate in the vacuum above the bound phosphocholine. And what we found was that the calcium oxalate actually bound to the phosphocholine. After about 12 picoseconds of simulation, the calcium oxalate actually collapsed onto the surface. And this bound with a formation energy of -10 electron volts, which was much more negative than when we just absorbed the calcium oxalate onto the absorbate-free surface, which is -7 electron volts. So that shows that the phosphocholine could actually encourage growth because this is more favorable than the free scenario before. So then we saw in the earlier images the fact that the organic is in between two layers of inorganic crystals. So we thought, could the phosphocholine head group actually cause these two crystals to bind together? So we placed this in a box with the two surfaces above and below. And what we found was the two surfaces actually fully encapsulated this phosphocholine molecule in the middle. And they actually attempted to redefine their crystallographic symmetry around this phosphocholine. And they did this with an absorption energy of -16.5 electron volts. This was much more favorable. And it can be suggested from this that the phosphocholine can in fact encourage kidney stones to grow. So what about inhibitors? How do they behave on these surfaces? So for the past 25 years, doctors have been prescribing potassium citrate as a treatment for kidney stones. But they don't know if the treatment is just the fact that it increases the pH and whether it does anything atomistically. So we looked at whether the potassium citrate behaves any differently on the surface. And what we found was that the potassium citrate binds to the oxalate groups on the surface first, and then it binds to the calcium ions as it has carboxylate groups, which act as calcium chelators in the citrate. And when this bound to the surface, we bound with a -8 electron volt energy, which was more favorable than the calcium oxalate binding onto the surface, suggesting that the citrate could actually bind preferentially over the calcium oxalate and potentially stop growth. So in summary, we found that the phosphocholine molecule can actually cause two crystals to agglomerate together. And actually we've shown that the potassium citrate is more favorable than the calcium oxalate shown in blue here, binding to the cod surface, suggesting that it could actually be an inhibitor. So in conclusion, if we could potentially stop the phosphocholine molecule binding to the cod surface, we could suggest a treatment for kidney stones of this type. You could either do that by developing a drug to bind to the phosphocholine, or by developing a drug to bind to the surface and stop the phosphocholine binding. This could be done by citrate. However, we need to do a bit more investigation to see whether the citrate could stop another surface coming and growing on top of it. Thank you.
So lastly, we have Vlad presenting, and we're stopping the live sharing for this talk. Yeah.
So, good afternoon, everyone. Welcome to the final session in stream 2 of the inaugural ResCompLeedsCon. I'm delighted that I'm going to be chairing this session. And first up, we've got Rose Collett. Take it away.
Thank you. So my PhD is called Multiscale Models of Fluid Transport for Characterizing Treatment Response in Breast Tumors. I'm part of the Fluid Dynamics CUT in my second year, so I've been working on this project for almost a year now. And I'm supervised by Dr. Zeke Taylor in SysTib and Professor David Buckley in the School of Medicine. It's not complicated.
You just click on the slide. So
the kind of overall aim of my project is to try and predict whether a breast cancer patient is going to respond positively or not to chemotherapy regimen. And we're trying to do this using a combination of medical imaging and maths. Why are we interested in breast cancer? Well, it's super common. It's the most common cancer in women across the world, and it's still a major cause of death. A lot of research has gone into it, and the outcomes really improved if you're diagnosed in the early stages. But unfortunately, the 5-year survival rate for stage 4 breast cancer, which is when it metastasizes and spreads to other parts of the body, that's only 28%. It's commonly treated using chemotherapy, surgery, or radiotherapy. So with chemotherapy, you can deliver the drugs either kind of off the bat before anything else happens, and that's called neoadjuvant chemotherapy. Then you can go to surgery, and you can also get chemotherapy delivered afterwards. The treatment that we're focusing on is neoadjuvant chemotherapy, so the first kind of treatment that occurs. It's the standard of care if you're a newly diagnosed patient with stage 2 to 3 breast cancer, then almost a third of these patients get given neoadjuvant chemotherapy. But however, as with any kind of cancer treatment, it really doesn't work for everyone. So only 39% achieve what's known as complete pathological response. Well, pathological complete response, which is basically when it works perfectly and the tumor entirely disappears. A full 12% of patients get no response at all, so the treatment was fully useless for them, and everyone else kind of lies somewhere in the middle. The tumor shrinks somewhat, but not enough, and you need to proceed to surgery. So if you are one of these patients that are non-responsive, you're suffering the side effects of your chemotherapy regimen with no benefits. Chemotherapy is unpleasant. It's not nice side effects. Some of them can last. Some of them are irreversible. Some women become infertile. So basically, it's really good to avoid going through a chemotherapy treatment if it's not going to work for you. And so the point of our research is to try and identify these non-responders as early as possible, so that instead of going through months of this chemotherapy, we can just stop it and try another treatment. And this leads us to a research question. So can we use a combination of medical imaging and mathematical models to predict, to identify non-responders and predict whether a patient is a responder or not? The way we propose doing this is through personalized oncology. The idea for this is that you need a mathematical model that's biophysically relevant, and we want to make it patient-specific because we said everyone responds differently. So we want to use MRI, magnetic resonance imaging, to take scans of a patient and use this data to kind of personalize the model. This is an example of a model that does this. So you take data, this is data before chemotherapy started, and this is after 1 cycle. And these are both used to parameterize the model, and you can get a prediction of what's going to happen. And you can compare this to another scan taken after the end of chemotherapy. And we see that this model works quite well. It's not perfect, but it works quite well. And this is kind of what we're building on. So other models that already do this, about 20 years ago, they used to do exponential models or logistic growth models, which worked quite well, but they were only one-dimensional, so they only modeled the growth in time. They couldn't take into kind of spatial effects. Reaction diffusion models are kind of what's most used nowadays, and the state of the art is a mechanically coupled reaction diffusion model. So the first equation here is the reaction diffusion equation. It describes the evolution of tumor cells in time with a diffusion component, which is the first on the left-hand side, and then a proliferation component. because the tumor isn't growing in a vacuum, it's growing in a breast. So the kind of surrounding healthy breast tissue kind of restricts the growth, and that's reflected in the second equation here, which couples the von Mises stress, which is a measure of the tissue stiffness, to the diffusion of tumor cells. And then lastly, we've just got an equation for a mechanical equilibrium. Most recently, this model was kind of improved to include the effects of treatment. And they did this by incorporating the temporal effects of drug delivery. And it's just one term down here added to the reaction diffusion equation. Here we've got on the top line the model that doesn't incorporate this drug delivery. The second line is the actual scan, and the third line is the fluid model. So I think that this one's a bit closer to reality. And basically model predictions improve when we kind of model the effects of the drug. And so we're trying to build on this by actually modeling the fluid flows. And the way that we're suggesting doing this is using a theory called multiple network pore elastic theory. This is really good for modeling biological tissue because basically you can model a solid matrix that's got lots of different types of fluid in it. And instead of trying to do a traditional like fluid structure interaction approach, you can treat the material as homogeneous and say that every single point you've got all the fluids and the solids. And that kind of makes things easier in this context. You define different compartments or networks for different fluids. So in our case, we're probably going to have a compartment for arterioles, venules, which are small veins and small arteries, and then capillaries, and then one for the interstitium. But this isn't, I've not really worked on this yet. It's probably going to start this work in December. So it's quite big at this point. And yeah, the data that we have to test our models on, this is a study that my supervisor David did a few years ago. So we've got 40 breast cancer patients who are undergoing this neoadjuvant chemotherapy regimen. And we've got data from before they started it and after one cycle, which we use to personalize the models. And then we've got data from afterwards that we'll be able to evaluate model performance on. A good thing about this is that we've got 40 patients, and the last model I talked about, they only tested 5 patients. So yeah, we'll be able to kind of try like evaluate patients that have different types of tumor. Yeah, and hopefully it'll work. That's it.
Fantastic stuff, thank you. And you're 2 minutes early, which is super. Fantastic. So next up, I've got Benaz El Haminia. I hope I got that right. Just set you up. This is your clicker. There you go. And I'll wave my piece of paper out. You've only got 1 minute after one.
Good afternoon, everyone. My name is Benaz, and I'm a third-year PhD student at School of Computing. Today, I'm going to be talking about one of the researches I've accomplished so far. First of all, I'll tell you what is the problem, and then how machine learning can solve this problem. And then I'll talk about the proposed method and our data set, and I'll share some of our experimental results and conclusion. I'm very happy that my cancer was treated, but it's very defeating sometimes that you can't join the regular activities of your friends, and my life revolves around my bowel movements. This is part of the story that Dana has shared on this website, and she shares how she suffers from the side effects of the radiotherapy. In fact, 86% of the patients with pelvic radiotherapy suffer from the side effects after their treatment. Clinicians still don't know why these patients get these side effects, how they get these side effects, what are the risk factors, and which organs in the bowel bag are involved in the toxicity. So in our research, we aim to create a machine learning system which is able to
analyze patient data, and then tell us if data is going to get toxicity and what are the risk factors for the patient to get this toxicity or side effects of the treatment, and which organs in the bowel bag is involved. So let's see what is inside this network. We propose multiple instance learning with attention neural network to predict bowel agency toxicity of the pelvic radiotherapy. Our input is two kind of data. We have CT scan of the bowel bag and those treatments. Then we divide each 3D volume into smaller cubes. This is called multiple instance learning. If I want to say it in a simple example, this is a typical neural network. We have one input, one output. We say this network can say if this is a cat or a dog. But in multiple instance learning, we have multiple instances, but only one output. For example, this is a classification network which says if there is any dog in this bag, yes or no. So we use the second idea for two reasons. First of all, you know that a deep learning model with huge 3D data can have million parameters to learn. So we use it and just train the network on a smaller cube, reduce the time and memory complexity. And the second one, we can use attention mechanism for this types of learning. With attention mechanism, we can say in this slide, where is the dog? So we say, yes, there is a dog, and instance number 8 is the dog. So we use this idea and then divide into smaller cubes, and then we pass them to two simple encoders, which are convolutional encoders, and extract the most important features from each cube, and then pass these features through two attention modules. These attention modules are simple feed-forward neural network, which compute the weight for us. The first one, the beta one, tell us which input is more informative. Is it CT or dose image, or it computes the weights for this one. The second one, or alpha, tell us which cube triggers the output, which one is the dog, actually. We're looking for the region of the toxicity. So after that, these attention modules give us weight, then the average weighted of the features pass through a classifier module. Here you see this, this one. And this has 4 fully connector layers, where the last one is activated by a softmax function to give us what is the output. So let's see what is the output of our network. In the middle pass, we have the toxicity, if this patient is going to get the toxicity, yes or no. And then analyzing alpha weights, here we can find the cube which is more involved in the toxicity. And analyzing beta weights, we can say, okay, dose is more informative or CT is more informative for toxicity. We trained our data set we trained our network on a data set with 315 patients, and then we divided them into 2 classes of patients without bowel agency and with bowel agency toxicity. Of course, we did some data pre-processing. Some patient had more than 1 treatment. You see that this patient had 4 treatment plans, so we had to combine and we scale the dose treatment to have only 1 person. We did registration and the region of interest for the bowel bag masking, and data normalization we did regarding to the whole population. We divided the data set into 2 subsets of train and test, and you know that 315 size is not good for deep learning, so we had to do something to avoid overfitting. We did data augmentation for the minority class, and then we used transfer learning. We trained 2 separate autoencoders on our CT and both data sets, only the trained data set. And then we transferred the weights on our encoder. So let's see what is the results of it. Here, when we trained our network on a scratch, that means no transfer learning, you see that the accuracy is 0.65. But when we transferred both encoders, we have 0.80, which shows that how transfer learning is important in our work. This applies to the other metrics as well.
This is also the area on the curve. You see that when we use transfer learning, it's 0.85, the best result, but without transfer learning or training from scratch, we have 0.75. So let's analyze the attention map to alpha and beta weight. This is A is the patient without bowel agency, and B is the patient with bowel agency. You see, when there is no bowel agency, the patient is not going to get any toxicity. The attention maps are scattered through the volume. You see that these blue cubes are everywhere, and there's no attention or focus of the network. But when we find the patient is going to get toxicity, all the attention maps are focused on the anterior side of the bowel bag. You see that here. To see then into 2D, we plotted them from slice number 5 to 34, from bottom to top of the bowel bag. And again, when there is no bowel toxicity, you see that this is the attention map, which is generated by our network. There is no red cube or attention. But for a patient with bowel agency, you see that some red cube on the anterior or right side of the bowel bag here. So we need to make a conclusion for all the patients. We computed the atlas toxicity. We registered all the patients into a reference patient, and then we got the average of all the toxicity map. And this is the average of irradiated dose, and this is the average of toxicity map. You see that the anterior side and right iliac fossa region, anatomical regions of the bowel bag is involved in the toxicity. This is the other view, and you see that the front side gets all the attention. To analyze the second attention module, we wanted to know dose is more informative or CT. We plotted them, the attention weights, alpha weight, to see which one is more informative. We see that for the slide number, for example, 10 to 0, the lower side of the bowel bag, both CT and those gain equal attention. You see that they have high attention. But as we go to the upper side of the bowel bag, those gain more attention, but CT gets less attention. In fact, the network says if I want to generate the toxicity, I look at lower parts of the CT and those, and then I look at the upper side. If I go back to this slide, you see that for the lower part, the shapes are different, so the network attends to them. But then for the upper side, the shapes are quite similar. So not much information here. So to conclude, I told you what is the problem, the Dana problem, how we're going to solve this. We propose to have a multiple instance learning with attention module to find which side, anterior and right iliac fossa are involved, and which input is risk factors. Those has a stronger predictor. At the end, I would like to say thank you to all my supervisors, and thank you for your time and your attention.
Fantastic. Thank you very much. Next up, we've got Amber Emmett. This is progress. That's together.
Lovely, thank
So if
you.
you understand, just
Great, thanks. Hi everyone, my name's Amber and I'm a third year PhD student in bioinformatics, and I'm supervised by David Westford and based in the Faculty of Biological Sciences. And today I want to talk to you about a computational method we're developing that takes different kinds of sequencing data sets and models how genes are regulated as one cell differentiates to another. And I'd like to start off by just explaining what gene regulation is and why it's so important. So all of you here have trillions of cells and they've all descended from one common ancestor. However, each of these cells have the exact same DNA code. So how can they diverge to produce all these different proteins and different functions with the same genetic blueprint? And the answer to that is each of these cell types will have different genes switched on and off. So nerve cells will express different sets of genes to red blood cells, and that's part of what makes the two so different. Now, gene regulation, so genes are regulated on multiple different levels, and what I'm interested in here is the first one here of transcription, when the DNA instruction manual is copied into a messenger RNA. And transcription is regulated by different DNA and protein factors. And what happens is often non-coding regions of DNA called regulatory elements are found by proteins called transcription factors. And these are recruited across long genomic distances at the site of transcription to either activate or repress gene expression. So in order to understand how a cell population differentiates, it's important to understand these complex interactions between regulatory elements, transcription factors, and genes. And now, since the advent of these high throughput DNA sequencing technologies, it's possible to do that using computational biology methods. There are now a variety of different sequencing techniques which measure different properties of DNA and RNA, and I'm going to talk about two of them here. So the first of which is RNA-seq here. And RNA-seq measures the transcription of every gene in the genome in a cell population, and using this we can quantify gene expression. And the second one I want to talk to you about is ATAC-seq. Now that stands for the assay transpose accessible chromatin, and it measures a property in DNA called chromatin accessibility. Now this is important because of the structure of DNA. So DNA is wound around these coarser proteins called nucleosomes, and this means that most of it's inaccessible. However, regulatory elements like enhancers, silencers, and promoters are clear to these nucleosomes since they need to be accessible to regulate transcription. So using ATAC, we can identify these regions of high accessible, which correspond to active regulatory elements. And also with ATAC-seq, we can measure transcription factor binding, and we can do this by identifying the DNA sequences in regulatory elements to which specific transcription factors bind. So from these two technologies, ATAC-seq and RNA-seq, you can generate these three data types, the gene expression, chromatin accessibility, and transcription factor binding. And what we've done is we've been working on this method that integrates these two sequencing data sets in order to identify transcription factors found this regulatory element across differentiation, and we call that method discrete. And here is an overview of the workflow with a short quick walkthrough. But briefly, the first two steps are all about generating inputs to the method from the sequencing files. And a lot of the steps in these processing pipelines are very memory intensive, so we perform them on the HPC. So thank you for the research there. So the first step is about identifying the regulatory elements and genes whose accessibility or expression changes as the cell differentiates. And following this, we take these differentially accessible regions and we look for overrepresented DNA sequences. And what these represent are the binding sites of transcription factors, which are important to specify lineage. And we can also identify the individual sites to which these transcription factors bind in the accessible regions. Now, following this, we match these transcription factor bound regulatory elements to nearby differentially expressed genes and consider, which ones regulate which gene. And we start with a community detection step. Now here, we look for regulatory elements which are bound by the same transcription factors and accessible in the same cell stages. And group them together using informal community detection. And what this is trying to do is trying to identify those interacting regulatory elements of transcription and transcription factors which may drive expression together. And that's what our last step is about. So what we do here is we try and predict the expression of each differentially expressed gene from the chromatin accessibility of each regulatory element community. And we do this using the C regression. And this step is for variable selection.
So what we do here is we eliminate regulatory elements predicted from the model, those that chromatin accessibility do not predict gene expression, and we select those whose chromatin accessibility does predict gene expression. And this way we're able to identify the transcription factors and regulatory elements which are whose activity is correlated to the expression of the gene and might regulate the gene. So that's the method, and it's a bit implementable within our package. Lots of steps here, it's available on the link there. And briefly to finish off, I want to describe how the method can be applied to try and understand how genes are regulated in differentiation. So the method's been applied to this data set here, which was generated by Dr. Ruben Tusa's group over at St James's. And what they've done is they've taken a matched ATAC-seq RNA samples from 3 biological replicates at 9 time points across this process here of in vitro B-cell differentiation. And we applied our methods to try and understand how transcriptional circuits are rewired as these cells are activated by invading antigens and stimulated to differentiate into antibody secreting plasma cells. And through creating these models, we've identified this set of transcription factors which are important to the lineage, just shown to them there. And we've done various other things. So we've linked them to clusters of cell-stage specific regulatory elements, as well as gene co-expression networks. And through doing this, we're able to see which transcriptional regulators that are active at what stage. And it's revealed some interesting things, such as the importance of this concept AP1 concept here, the transcription factor concept, transcriptional reprogramming, B-cell activation. You know, it's an example of how we can find the underlying biological signals from these really big noisy data sets. So just to summarize quickly, so gene regulation is important for programming how cells differentiate, and on the transcriptional level, it's controlled between these interactions between cis regulatory elements and transcription factors. And what we've done is we've worked on this method, which integrates sequencing data sets in order to identify and prioritize those that are important to the differentiation process. And we've applied them to this, this study of B-cell differentiation and use it to understand how genes are regulated in this process. So thank you all for listening, and of course, a big thank you to everyone that worked on this project, including my supervisor, David Westhead, and all our collaborators here, and of course, the BDSLC's White Rose DTP for funding.
Fantastic. Thank you very much. Next up, we got Patricia Tienes.
Not sure if you are with the right version of the presentation.
Oh, you're going to tell me now. Is that doable?
Yeah, I can work with whatever.
You can work with whatever.
Yeah. I need to stay here, or can I walk?
Stay here. That's okay.
I like to walk.
Like, I mean, if you can be loud back to the microphone, that's fine. Just.
Oh, I see. I need to put my beautiful face here.
You do, yeah.
Okay.
So forwards, backwards.
Okay.
Okay.
Oh,
10 minutes.
can I start?
Absolutely.
Okay. So, slightly different talk today. I'm not going to present a piece of my research, but I'm going to talk about a problem that a lot of us are facing, or at least face it at some point. So basically, I think the time frame, it's pretty much the same all the time. We realize that we can answer a research question using coding. So we decide what programming language you want to use. We go through a training, we learn the syntax, and we think, oh, I know how to print hello world. I can solve my problems now, because now I am a software developer. And then we come back, look our problem, our research question, try to solve, and we fail. Outside, it's like that. So people are coming and
talk with me and say, Patricia, I learned how to code, I memorized the syntax. And then I go through my research question, I try to develop a software and I failed. I cannot do this. I think coding is not for me. Guys, there is no such thing like coding is not for me. The huge problem here is that our learning process is not just memorize a syntax and then develop a software. We need something between these two things. We need to develop a problem-solving skills to fill the gap between these two ends. Without doing this, we are not going to be able to use any kind of language to solve any kind of problem. So my talk today, it's about how we can, it's some tips to help us to develop these problem-solving skills. That's going to connect the two ends between memorize the syntax and develop our software, our piece of software. So my tips are going to be basically between two categories. So you should follow a framework and you should practice it. So the framework, you can try solve your problems randomly. It's a way. You can try, it's wrong, try again. Oh, now it's right. But I think have some kind of consistency is very, very important. And you are going to have this if you follow some kind of framework. So create a set of steps that you are going to follow every time that you have a problem. The thing here is that people think differently. So don't look this as a framework, look this as tips. And then I think in one way, you think in another way. This is important, the diversity is important. So just try to use these tips to improve your framework somehow. My first tip, understanding. People came to me and say, Patricia, I need to use the method A to find B, and I have a problem. Can you help me? And I say, yeah, indeed I can. So come on here, sit, look at me and explain to me, what is your problem? And the person, I need to use A to find B. No, it's not how. It's what is your problem? What is your question? And then the people look at me and say, give me a week because I need to figure out. And I say, okay, go and think. So before move for coding, for solving our problem, first discover what is your problem about. And we are talking about computer stuff. So we also need to understand what are our requirements, so technical stuff. What language we are going to use. Our program is going to run on HPC or in our personal laptop. So these are technical stuff. To help figure out your main question and your technical stuff, I have two tips. First one, write down. Create diagrams, flow charts, things like that. It's going to help you to visualize your problem, and you're going to find better your question between your huge mess. So put down, okay? The second question, I'm not crazy. I'm saying to you, grab your Hubbard duck. So have a small object, look for the object and explain for the object your problem. This is indeed a technique between the software developers. If you are not very comfortable with this, you can talk with your supervisor, a colleague, or even with me, no problem. Just have a Hubbard duck, okay? Any kind of thing. The idea behind this technique is that if you try to explain your problem for someone that doesn't have any clue about what you're talking about, you're going to do this in the most simple way possible. And when you do this, you create some kind of better understanding of your problem because you are just able to explain something if you understand something. So sometimes the best way of learning something is teaching. So grab your Hubbard duck and talk with it. Okay, second tip, very good, divide. Reduce, divide, and simplify. if you try to solve your big question, your big problem at once, you are going to cry, suffer a lot. No way, this doesn't work, okay? The best way you can do to solve a big problem is break down your problem in small problems. Then you solve every small problem individually, and finally you can put everything together. This is good from the problem solving point of view, and this is very good from the coding point of view. So a good code always have small parts. So this is good from the both sides. And the gold tip here is the simplified. Sometimes we have the big problem, we break down in small problems, but even though we look at that small problem and how to solve this thing, no problem, it's common. So what you can do is simplify. For example, let's think our job is to print Fibonacci sequence, and we want to print 100 items, and you don't know how to do this. So instead of print 100, you start printing 2 items, and then 3, and then 4. At some point, you're going to figure out the main idea behind that problem, the main logical behind that problem, and then you can expand and solve everything. So break down your big problems in small things and simplify all the time that you need. Okay, I did everything you said, Patricia, but I am stuck. So first things first, welcome to my normal day. Coding is be stuck, okay? I know a lot of people that came to me crying and say, every time that I try to code something, it's a lot of errors and I'm stuck and I'm so bad on this. No, you're just normal on this. Be stuck in this part, okay? Don't worry, you are not wrong, you are not bad, it's just the way. Actually, it's the way I know, sorry. Gold tip for this part is take a break. Please take a break. Go take a coffee, go for a walk, anything. Just don't think in your problem anymore. You need a fresh mind to work. Take a break. Second tip, after a break, you can come back and then you can start to debug your code. Basically, line by line, you are going to verify if what you said for your computer, it's what you want to say for your computer, because sometimes you say A and we want to say B, for example. So be sure that you did everything right. I did everything right. My answer is still wrong. Take a step back. Take a step back. So sometimes we just need think again, grab your rubber duck, think again in your problem, because sometimes we think we understood our problem, but you didn't. And a very nice thing, sometimes you just need to delete everything. Yeah, put everything down and start again. So the worst part you already did is thinking about. The code is just the translation between your mind and your computer. So sometimes you just need a fresh page and start again. Research. This could be on the last slide. So if you're stuck, please do a lot of research. Someone else had the same problem. So the answer is over there, is you just need to find. But I think you should research in every stage, because research is going to find you to understand better your problem, to find new ways of solving your problems and whatever. So do a lot of research, practice, and practice is the only way of become good in this thing. And just one more second. If you need a rubber duck, I can be your rubber duck. Part of my job is giving support for the researchers. So if you need me, you can contact me by my email, or you can even try another colleague in the research computer team. They are better than me. So what's that? Thank you very much, guys.
Should have brought a rubber duck with you. That would have been.
But no, that was
mine in Brazil. Sorry.
you lived was in Brazil.
Yeah.
We'll sort that out. Thanks so much. Great. So that brings us to the last talk of the day, which is a recording, which we won't be live streaming. So if you're joining us via the live stream, this is the end for stream 2. Thanks for joining us. See you soon.